Okay, so we're gonna modeling with combined equations, and they've given us a scenario of someone skiing down a hill. It says that they're at a 100-meter hill. The hill slope is -1, so it has a constant slope on the hill. So we have some slope like this, but there are moguls on the hill. So if it's sloped downwards, essentially the moguls create this type of effect. And they measure 1.5 meters from the peak to the trough, and the moguls are 5 meters apart. So essentially, what it's showing right now is the type of equation we have. They're going up and down over the moguls, but constantly heading downwards. Now we know our sinusoidal functions are completely horizontal, right? And to have a slope like that, we have a linear function. So the idea is we're probably going to be combining a linear and a sinusoidal function. So what we're going to want to do is essentially figure out what the equations are for both of them and combine them together. So let's scroll down just a little. Let's get an idea of our first equation here. I guess I'll add a little picture in. We have a linear function. Scale of 1 would be good. Actually, here we go. Scale of 1. They said we had a 100-meter hill. So we'll say that this instead of 10 is 100, right? So we're at the top of the hill, and it has a slope of -1. And we'll say these are going by 10s instead of 1s. Okay, and we'll do the same with the x-axis. So the idea here is that this is our time, and this is our distance from the ground, right? So we'll call this d, our distance from the ground. So in terms of our slope, because it's going a slope of -1, in other words, you kind of travel at 1 meter per second, you have a constant slope like this. Okay, so what that means is our points across this, we know that our linear functions are y equals mx plus b, right? Our m being the slope, which we already know the slope is -1, we said. And the y-intercept, well, the y-intercept is just the top of the hill, which is our 100. So this is the equation of our linear function. Y is equal to -x plus 100. Okay, so we'll call it equation 1. The second part of our function, let's say, so that kind of deals with this. This is the linear part. We'll break this into the sinusoidal part, okay? We'll just call it the sinusoidal part. There are moguls that measure 1.5 meters from the peak to the trough. Okay. Essentially what that means, and I should get a different type of graph here. Let's kind of bring up a sinusoidal graph. I guess we can do it in degrees. They might want it in radians, actually, but let's bring this up in degrees. Actually, doesn't matter. They cover that part. Okay. What they've told us, from the peak to the trough is 1.5 meters. So whatever it is, essentially, imagine this is the idea. Here's 1, so 1.5 would be roughly here. Okay, so from here to here, this is our range. Our range of the function is, oh, sorry, they say it's 1.5 meters. Oh, sorry, I doubled it instead. The amplitude is not 1.5 meters. The range is 1.5 meters. So if the range is 1.5 meters, thus the total distance, the amplitude would be half of that. Okay, so if our range is 1.5, we'll call it the A, the amplitude would be 1.5 divided by 2, which is going to give us 0.75. So in other words, we have probably about there as our entire range of the sinusoidal function. Right? We also need to figure out, and I guess I'm going to have to change this part of it, the period of this function. The period of this function is going to be over the course of, what did they tell us up here, 5 meters apart. So from peak to peak is 5 meters apart. So maybe degrees wasn't the best one to use. That's okay. We'll kind of replace these. We'll go by. Have these in meters, okay? And then 25. Good. So let's just go on the saying that if it's from our peak to our trough, if this x is, again, our distance to the middle of the mogul, it'll go up and down across this function. Okay, so we're not going to actually transform this sinusoidal function anywhere up or down. So in other words, the d value at the end, if we had y is equal to sine x plus d, we're just going to keep that at 0 and just assume this is the middle of the mogul, okay, in terms of our height. and the distance across it is from our peak to our peak. So, of course, we could use a cos function to do it. I think we want us to use sinusoidal. So if this would be the middle of the function, it takes 5 seconds for this function to go up, down, and come back to where we are. So it would go up, cross back down here, and come back to here. This would be the period of one of the functions. It takes 5 meters, they said. So it takes 5 meters for us to go over it, come back down to where we started, go back down to the trough of the function, and back to where we were. So for our sinusoidal function, we're really just looking at y is equal to the a value of sine, and I think you guys call it k. Mm-hmm. K at x. Okay. If we're going to do it in meters, our a is pretty straightforward. Our a is always whatever our amplitude is. So in this case, it's 0.75. So we know the function is going to start by saying y is equal to 0.75. Okay. Our k value is just a little bit harder to calculate. Our k value times x. Our k value is normally a period takes 360 degrees. Okay, or we could say 2 pi. We have 2 options for that. So your k can be either 1k is equal to 360 degrees, or we could say 1k is equal to the idea of 2 pi in terms of our distance. Now, if we were to keep it in degrees, our idea here is we want it to reduce to the value of 5. So we want 360 to be equal to 5. So that would be like saying, okay, so we would say we'll build our equation. We'll kind of hide this because we kind of brought it up off the board. But our idea is that if k is equal to 1 period of the function, and we know that in a normal 1k would be, the period of function would be 2 pi, our new value has to be what? In our case, it would be pi. And you can rebuild that same equation with degrees, saying k is 360 degrees, k is equal to 1 period, and we have to now build it to 5. Okay? So our new function for k, we just bring our 2 pi over. K ends up being 2 pi over 5. And in our degrees function, k would end up being 360 over 5, which actually gives us a value. What would end up being? 72? I think that's what it is. 7 is 35, 10 is 2. So k is 72. So if we're in radians, this is our new k value. And if we were in degrees, this is our k value, right? So with that being said, our new function would end up being what we have here. Y is equal to 0.75. There's our amplitude. And for radians, we have 2 pi over 5 x. And for degrees, the amplitude doesn't change. It's still the same. The only difference is we use 72 times x. Okay? And we'll look at what those two functions look like quickly. So here's our one when it's in radians. And our other function read negative x plus 100, I believe, right? So we kind of have to zoom out quite a bit, and it'll kind of get rid of our sinusoidal function here. You won't be able to really see the bumps. But here's the idea. So these are the two functions, but we have to combine the two together. So to combine the two together, I essentially have our negative x plus 100, and then plus our 0.75, 2 pi over 5 times x.
Sine 2 pi?
Oh,
0.75 sine.
Yes,
Yeah.
thank you. I was wondering what was it. There we go. So we'll now have our sine wave, but following the linear function of what we had before. So let's get rid of the blue part so that we can see that this is what it would look like to ski down that mogul hill when we combine the two functions. It has the bumps of that same sinusoidal function down here, but the slope of the original linear function that we first started with. Does that kind of make sense? Mm-hmm. Okay.